30 seconds and counting, all systems nominal. The date is April 11, 1970, and America is about to launch its third mission to land men on the lunar surface. 25 seconds, engine start sequence initiated. Inside the massive Saturn V rocket, 3 astronauts sit ready to continue mankind's greatest adventure. 12, 11, 10, 9, ignition sequence start. But what begins as a routine flight to the moon will become one of the most dramatic rescue missions in human history. 2, 1, we have liftoff. A mission that will test the limits of human ingenuity, courage, and the will to survive against impossible odds. Tower clear. This is the story of Apollo 13. The year is 1970, and America's Apollo space program is in full stride. Just 9 months earlier, the entire world watched in awe as Neil Armstrong and Buzz Aldrin became the first human beings to walk on another world. That's one small step for man, one giant leap for mankind. The impossible had been achieved. President Kennedy's bold promise to land a man on the moon before the decade's end had been fulfilled, with 5 months to spare. 4 months after Apollo 11's historic landing, Pete Conrad and Alan Bean successfully touched down in the ocean of storms during the Apollo 12 mission, proving that the first landing was no fluke. America could reliably send men to the moon and bring them home. The system worked. The procedures were solid. Space travel, it seemed, was becoming almost routine. But routine is a dangerous word in spaceflight, and the crew of Apollo 13 is about to discover just how quickly triumph can turn to catastrophe. The mission is commanded by James Arthur Lovell Jr., a veteran of 3 previous spaceflights. At 42 years old, Jim Lovell is one of NASA's most experienced astronauts. He flew with Frank Borman on Gemini 7, completed the Gemini program alongside Buzz Aldrin on Gemini 12, and was part of the historic Apollo 8 mission, the first to orbit the moon on Christmas Eve 1968. Lovell backed up Neil Armstrong on Apollo 11, and now finally, he's getting his chance to walk on the lunar surface. This will be his 4th journey into space, and if all goes according to plan, he'll become the 5th human being to set foot on the moon. Flying alongside Lovell are 2 rookies, men who have trained for years but never actually flown in space. Ken Mattingly is assigned as command module pilot, responsible for piloting the Odyssey spacecraft and conducting scientific observations while his crewmates explore the lunar surface. Fred Haise, a former Marine pilot and test pilot, will serve as lunar module pilot, accompanying Lovell down to the moon's surface in the Aquarius lunar module. For both Mattingly and Haise, this represents the culmination of years of preparation, the realization of every astronaut's dream. But just 1 week before launch, disaster strikes the crew before they even leave the ground. During a routine training session, backup crew member Charlie Duke is exposed to German measles. It's a seemingly minor issue, but in the confined environment of a spacecraft 200,000 miles from Earth, even a common childhood disease could prove catastrophic. Medical tests reveal that both Lovell and Haise have immunity to the disease, but Mattingly does not. The medical surgeon makes his recommendation. Mattingly must be pulled from the prime crew. The decision falls to Lovell as mission commander. Does he stand by his crewmate and risk the entire mission, or does he accept a replacement pilot he's barely trained with? It's one of the hardest decisions of Lovell's career, but ultimately, the mission must come first. Ken Mattingly is devastated, pulled from his first spaceflight just days before launch. His replacement is Jack Swigert, the command module pilot from the backup crew. Swigert is a capable pilot, but he's never trained extensively with Lovell and Haise. The prime crew has been broken apart, and time is running out. The mission objectives for Apollo 13 are among the most ambitious yet attempted. Previous Apollo missions landed in the relatively flat and safe Mare regions of the moon, the dark plains visible from Earth. But Apollo 13 is targeting a much more challenging site, the Fra Mauro Highlands, a region of rough hilly terrain near a massive impact crater. Scientists believe that the ancient impact that created this crater excavated material from deep within the moon's crust, throwing it across the surface. By collecting samples from this region, the crew could provide crucial insights into the moon's formation and early history. Lovell and Haise will deploy a sophisticated scientific package, including a heat flow experiment that requires drilling 3-meter-deep holes into the lunar surface. The drill, specially developed by Black & Decker, represents a significant technological leap forward. Apollo 13's mission patch bears the Latin phrase, ex luna scientiae, from the moon, knowledge, reflecting the crew's commitment to the scientific goals of the mission. But all the scientific planning in the world cannot prepare them for what's about to happen. Launch day arrives, April 11, 1970. Despite the last-minute crew change, the mission proceeds on schedule. At Launch Complex 39A, the massive Saturn V rocket stands ready, 363 feet of controlled power, the most powerful machine ever built by human hands. Inside the cramped command module at the top of this tower, Lovell, Haise, and Swigert run through their pre-launch checklists. The tension of the crew change has given way to professional focus. They have a job to do. T-minus 60 seconds and counting. All systems are go. The final seconds tick away. 15, 14, 13, 12, 11, 10, 9. Ignition sequence start. The 5 massive F1 engines of the Saturn V's first stage ignite in sequence, building up to 7.6 million pounds of thrust. 6, 5, 4, 3, 2, 1, 0. We have liftoff. At 2:13 p.m. Eastern Time, Apollo 13 rises from the pad, faster and faster, climbing on a pillar of flame. Houston, we have tower clearance. Roger that, 13. You are go for staging. The launch is picture perfect, or so it seems. 5.5 minutes into the flight, the crew feels something wrong. Unusual vibrations shake the spacecraft. Houston, we have inboard engine shut down. The center engine of the second stage has cut off 2 minutes ahead of schedule. For a moment, uncertainty grips both the crew and mission control. Has something catastrophic happened? Will they make it to orbit? But the other 4 engines compensate, burning longer to make up for the lost thrust. Houston, 13, what's the story on Engine 5? Jim, we don't have a story on the early shutdown, but the other engines look good, and you are go for orbit. The crew breathes easier, but they don't know how close they've come to disaster. Unknown to anyone at the time, the Saturn V has been experiencing severe pogo oscillations, violent vibrations that flex the rocket structure at its limits. The center engine's automatic shutdown has actually saved the mission. Had the vibrations continued for just a few more seconds, the entire vehicle could have shaken itself apart. Apollo 13 and its crew would have been lost before ever reaching space. But none of this is known yet. As far as anyone can tell, it's just a minor anomaly, nothing to worry about. The next 2 days proceed flawlessly. Apollo 13 speeds toward the moon at thousands of miles per hour, coasting through the void on a carefully calculated trajectory. The crew settles into the routine of spaceflight, eating, sleeping, conducting housekeeping tasks, and occasionally broadcasting television shows back to Earth. But public interest in the mission is tepid at best. The networks are reluctant to interrupt regular programming for what many Americans see as just another moon flight. Haven't we already done this? The Vietnam War dominates the headlines. 3 astronauts flying to the moon for the 3rd time seems almost mundane. If only they knew what was coming. 55 hours into the mission, the crew conducts another television broadcast. Jack Swigert gives viewers a tour of the command module, showing off the navigation equipment and demonstrating how the crew prepares food in zero gravity. Fred Haise moves into the lunar module, Aquarius, and shows how he'll set up his sleeping hammock on the lunar surface. Lovell narrates, relaxed and professional. He's done this before. This is his 4th spaceflight, and everything is going exactly according to plan. The broadcast lasts 49 minutes. Okay, Houston, we think we ought to conclude it from here. Roger, Jim, it's been a real good show. We're just about ready to close out our inspection of Aquarius and get back for a pleasant evening in Odyssey. Good night from the crew of Apollo 13. The television cameras shut off. The crew begins stowing equipment and preparing for their sleep period. Everything is nominal. Everything is perfect. 7 minutes later, Mission Control radios up a routine request. 13, we've got one more item for you when you get a chance. We'd like you to stir up your cryo tanks. The cryogenic oxygen and hydrogen tanks in the service module need to be stirred periodically to prevent the super-cold liquids from stratifying. It's a completely routine procedure, performed on every Apollo flight. Jack Swigert, alone in the command module, while Lovell and Haise are still in the lunar module tunnel, reaches for the switches. "Okay, Houston," he acknowledges. He flips the switches to activate the fans inside Oxygen Tank 2. And in that instant, everything changes. A loud bang reverberates through the spacecraft. All three astronauts feel it, a sharp jolt that shakes the entire vehicle. What was that? For a moment, there's confusion. Fred Haise is still in the tunnel leading to the lunar module. Jim Lovell is halfway between the two spacecraft. Jack Swigert is in the command module. All three have felt the same thing. "Okay, Houston," Swigert radios, key professional despite his concern. "We've had a problem here." In Mission Control, the flight director looks up. "This is Houston, say again, please?" And now Jim Lovell's voice comes over the radio, more urgent. "Houston, we've had a problem. We've had a main B bus undervolt." In the Mission Operations Control Room in Houston, Texas, controllers stare at their screens in disbelief. Data is coming in from the spacecraft, but it doesn't make sense. It can't be right. Fuel cell 1 and 3 are offline. Both of them? That's impossible. We're showing O2 flow on fuel cell 1 and 3. Pressure dropping. Something is terribly, catastrophically wrong. The astronauts don't know it yet, but the spacecraft is dying around them, and they're 200,000 miles from Earth, still heading away from home toward the moon. What has happened? Inside Oxygen Tank number 2 in the service module, a chain of unlikely failures stretching back years has finally reached its terrible conclusion. The tank, manufactured and tested long before the Apollo 13 mission, had been installed in the Apollo 10 service module, then removed for modifications. During this removal, the tank was inadvertently dropped, potentially damaging internal components. No one noticed. The tank was reinstalled in the Apollo 13 service module. During pre-launch testing at Kennedy Space Center, engineers tried to drain the oxygen tanks but found that Tank 2 wouldn't empty properly. The damaged internal fill line was allowing oxygen to leak back. To solve this problem, engineers decided to boil off the oxygen by running electrical heaters inside the tank. But the thermostatic switches that should have regulated these heaters had been damaged by an electrical design change years earlier. The heaters ran much hotter than designed, reaching over 1,000 degrees Fahrenheit. The extreme heat damaged the Teflon insulation on the wiring inside the tank. Again, no one noticed. The tank passed all its tests and was declared flight ready. Now, 56 hours into the mission, when Jack Swigert activates the stirring fans, the damaged wiring inside the tank arcs and sparks. In the pure oxygen environment of the tank, under high pressure, the spark is all it takes. The Teflon insulation catches fire instantly. In seconds, the fire spreads, heating the oxygen to extreme temperatures. The pressure inside the tank skyrockets. The tank structure cannot contain the forces building inside it. With explosive force, Oxygen Tank number 2 ruptures. The service module is ripped open. A 13-foot panel is blown completely off the spacecraft. High-pressure oxygen, precious oxygen needed to keep the crew alive, vents into the vacuum of space. The shock of the explosion damages fuel cells 1 and 3, cutting off most of the command module's electrical power. It also damages Oxygen Tank 1, which begins leaking its contents as well. In moments, Apollo 13 has gone from a routine flight to a life-or-death emergency. But the crew doesn't know all this yet. They're trying to understand what has happened. Jim Lovell looks out the window and sees a disturbing sight. "It looks to me like we're venting something out into space," he reports. "It's a gas of some sort." His words are calm, but inside, his concern is growing. Jack Swigert is checking the instrument panel. The fuel cell oxygen pressure readings are dropping fast. One gauge reads 0, the other is falling steadily. We've lost O2 tank 2, and tank 1 is going down too. In mission control, the realization is setting in. This isn't a sensor malfunction. This isn't a minor problem. The spacecraft is bleeding its lifeblood into space, and unless something is done immediately, the crew is going to die. Flight Director Gene Kranz, a Korean War veteran known for his unflappable demeanor and steely resolve, surveys his team. "Okay, people, listen up," he says, his voice cutting through the noise. "We've got a serious situation here. Let's work the problem. Don't make it worse by guessing." He turns to his ECOM, the electrical and environmental systems engineer. "How much time do we have?" The answer comes back. "Based on current leak rates, oxygen tank 1 will be empty in less than 2 hours. When that happens, fuel cell 2 will die. The command module will be completely without power. And gentlemen," Kranz says, "without power, we have no life support, no guidance, no way home." The men in this room, the flight controllers, have trained for emergencies. They've run countless simulations, practiced failure scenarios, prepared for the worst, but no one has ever imagined this. The combination of failures is unprecedented. Still, this is NASA. This is mission control. These are the people who put men on the moon. If anyone can save Apollo 13, it's them. In space, Jim Lovell is reaching the same conclusions as mission control. He's been flying spacecraft since 1965. He's logged more time in space than any other astronaut. He knows these systems inside and out, and he knows, looking at the gauges, that they're in terrible trouble. The command module cannot survive. Within 2 hours, maybe less, it will be a dead hulk. But Apollo 13 carries another spacecraft, one with its own power, its own life support, its own everything. The lunar module Aquarius, designed to keep 2 men alive on the moon for 2 days, might just be able to keep 3 men alive in space long enough to get home. It's their only chance.
"Houston," Lovell radios, "we're going to have to think about powering up the LM. "Roger that, Jim," comes the reply. "We're working on procedures now. But there's a problem. The lunar module takes 3 to 5 hours to power up using normal procedures. They don't have 3 to 5 hours. They have maybe 90 minutes before the command module dies completely." In Houston, teams of engineers are frantically developing abbreviated power-up procedures, cutting every possible corner, streamlining every step. They're doing something no one has ever done before, improvising on the fly, creating new procedures in real time, and they're doing it while 3 men's lives hang in the balance. In the spacecraft, the crew is moving fast. Fred Haise floats into the lunar module and begins throwing switches, bringing systems online. Jack Swigert stays in the command module, trying to preserve every amp of battery power, shutting down non-essential systems. Jim Lovell is between them, coordinating, making decisions. They need to transfer the alignment from the command module's guidance system to the lunar module's computer before they lose power. Without this alignment, without knowing precisely which way the spacecraft is pointing, they'll have no way to fire the engine accurately. They'll be lost. Jack calls out numbers from the command module computer. Fred punches them into the lunar module. "Hurry," Jim urges. "We're running out of time." All around them, the spacecraft is dying. Warning lights are illuminating. Alarms are sounding. The oxygen pressure gauge for Tank 1 continues its steady, inexorable drop towards 0. They're in a race against time, and they're losing. But the crew is good. They're professionals. They're test pilots who have spent their entire careers dealing with emergencies, making life-or-death decisions in seconds. 90 minutes after the explosion, the lunar module is powered up. The alignment is transferred. The command module is shut down to preserve its batteries for re-entry. Against all odds, they've done it. They've stabilized the situation. They're alive. For now. In mission control, Gene Kranz looks around the room. Okay, he says, we've bought ourselves some time. Now we need to figure out how to get them home. He calls a meeting of his team leaders. The situation is this. The service module is crippled. Its main engine cannot be trusted. Even if it could be fired, no one knows the extent of the damage back there. The explosion might have damaged the command module's heat shield, the one thing absolutely essential for surviving re-entry. There's no way to know until they jettison the service module, and they can't do that until just before re-entry. The command module has no power except for its batteries, which must be saved for re-entry. The only operational systems are in the lunar module, so the question becomes, how do we use the lunar module to get them home? Here's where years of contingency planning pay off. NASA has always been paranoid, in the best way possible. For every system, there's a backup. For every procedure, there's an alternative. Early in the Apollo program, engineers asked themselves a question. What if the main engine fails? What if we need to use the lunar module to get home from lunar orbit? It seemed far-fetched, but they studied it anyway. They ran simulations, they developed procedures, and now, incredibly, impossibly, they need exactly those procedures. The lunar module becomes a lifeboat, a role it was never designed for, but one it must now fulfill. Before the explosion, Apollo 13 had maneuvered off the free return trajectory. This was standard procedure for later Apollo missions, allowing them to reach more interesting landing sites. But now, being off the free return is a death sentence. If they don't get back on that trajectory, the moon's gravity will capture them in lunar orbit and they'll never get home. They need to burn the lunar module's descent engine to correct their course. It's another thing they've never done before, flying the docked command module and lunar module as one unit using the LM's engine. The LM was designed to land on the moon, not push around the much larger command module. Can it even be controlled? They're about to find out. Mission Control works out the burn parameters. In space, Jim Lovell and Fred Haise configure the lunar module. The burn has to happen soon, before they get too close to the moon, before the trajectory gets too bent. Okay, Aquarius, you're go for the burn. Roger, go for burn. Lovell's hand is on the throttle. He's flown to the moon before, but he's never done anything like this. 30 seconds. The engine ignites. The spacecraft lurches, begins to drift. Lovell fights the controls trying to maintain attitude. It's like flying a truck, he'll say later. But he's a test pilot. Flying trucks is what he does. Burn complete. Shutdown. They've done it. They're back on the free return trajectory. The moon will now slingshot them back toward Earth. They're coming home.
But the relief is short-lived. They're still days away from Earth. The lunar module was designed to support 2 men for 2 days. Now it has to support 3 men for 4 days. The consumables, the oxygen, water, power, everything is going to be stretched to the absolute limit. In Houston, engineers are doing the math. It's not good. At current consumption rates, they'll run out of water before reaching Earth. They need to shut down every non-essential system in the lunar module, power it down to the bare minimum. The crew complies. They shut down the guidance computer. They turn off the heaters. They turn off everything except the absolute essentials. The lunar module, one of the most sophisticated machines ever built, is now operating on less power than a vacuum cleaner. And it's getting cold. Without the heaters, without the waste heat from all the electronics, the temperature in the spacecraft begins to drop. 40 degrees, 35 degrees, 30 degrees. The crew is shivering. They're wearing their lunar boots, pulling on extra underwear, anything to stay warm. Water condenses on the cold walls, drips from the windows. Jim Lovell reaches into the storage locker for food, and it's like reaching into a freezer. They're not just cold, they're miserable. Sleep becomes nearly impossible. They're exhausted. They've been working non-stop since the explosion, but they can't rest in this frigid environment. And they're dehydrated too. To conserve water, they're drinking only 1/5 of their normal intake. The combination of cold, fatigue, and dehydration is taking its toll.
But cold is the least of their problems. As the crew settles into their new routine, as the hours pass and Earth remains a distant blue marble, a new crisis is brewing. They're breathing. That sounds obvious, but every breath they take is a problem. Humans breathe oxygen and exhale carbon dioxide. In a sealed spacecraft, that carbon dioxide builds up. Too much CO2 is toxic. It causes headaches, confusion, drowsiness. Eventually, at high enough concentrations, it kills you. Every spacecraft has a system to scrub CO2 from the air. The Apollo spacecraft use lithium hydroxide canisters. Air passes through the canister. The lithium hydroxide chemically absorbs the CO2, and clean air comes out the other side. But the canisters have a limited capacity. Once they're saturated, they're useless. The lunar module has its own CO2 scrubbing system, but remember, it was designed for 2 men for 2 days. With 3 men breathing, the canisters are being overwhelmed. Mission Control watches the CO2 levels creeping up. They're going to hit dangerous levels in hours. And here's the cruel irony. The command module has plenty of spare lithium hydroxide canisters, but the command module is powered down. Its scrubbing system can't be used, and even if it could, the canisters are the wrong shape. The command module uses square canisters. The lunar module uses round ones. You can't just swap them. It's the ultimate square peg in a round hole problem, literally. In Houston, a team of engineers is assembled. Their mission is simple to state, impossible to achieve. Figure out how to make the square command module canisters work in the lunar module system, and do it using only materials available to the crew on the spacecraft. The clock is ticking. CO2 levels are rising. The crew is already reporting headaches. Ed Smiley and his team gather in a conference room. They dump out a box containing duplicates of every item on the spacecraft: plastic bags, cardboard, duct tape, hoses from the spacesuits, a sock. They know the inventory by heart. Everything that went into the spacecraft was logged, listed, accounted for. Now they have to be creative. They start experimenting. Take the square canister. Put it in a plastic bag. Attach the spacesuit hose here. Use duct tape to seal it. Try to create airflow through the canister. Hour after hour they work. Coffee goes cold. Ashtrays fill up. This is 1970 and everyone smokes. They try configuration after configuration. Finally, they have something. It's not pretty. It looks like something cobbled together in a garage, but it works. Air flows through the command module canister. CO2 is scrubbed. The engineers test it, retest it. It holds up. Now comes the hard part. They have to explain to the crew how to build this contraption. Remember, the crew is pulled, exhausted, stressed. They can't show them a picture. They have to describe it over the radio, step by step. Okay, Jim, this is going to look like a mailbox when you're done. We're going to need the square lithium hydroxide canister from the command module. You'll need a plastic bag. The LCG bag will work. You'll need duct tape, a lot of duct tape. You'll need the hose from Fred's spacesuit, and you'll need a piece of cardboard from your flight plan book. Jim Lovell and Fred Haise listen to the instructions and start assembling. Cut the tape this long. Put it here. No, the other way. Seal this edge. Make sure it's airtight. It takes an hour. It's tedious, frustrating work. But finally they have it. A Rube Goldberg contraption of plastic and cardboard and tape. They connect it to the lunar module's air system. They hold their breath, and it works. The CO2 levels start dropping immediately. Another crisis averted. Another impossible problem solved. As Apollo 13 swings around the moon, passing over the lunar far side where no radio signals can reach, the crew has a moment to reflect. Out their window, they can see the moon's surface passing below. They're so close. Fra Mauro, their intended landing site, is down there somewhere. Jim Lovell was supposed to walk on that surface. This was supposed to be his mission, his moment. Instead, he's in a crippled spacecraft, fighting for survival. The irony isn't lost on him. He's been to the moon twice now, and he'll never set foot on it. But right now, he just wants to get home. He just wants to see his wife and kids again. The spacecraft emerges from behind the moon. Radio contact is restored. Houston, Aquarius, we're back. Roger, Jim, we've got you. You're looking good. They're on the way home now, but they're still days away from Earth. The trajectory is good, but not perfect. They're drifting slightly off course. If they don't correct it, they'll hit the atmosphere at the wrong angle. Too shallow, and they'll skip off the atmosphere like a stone on water, flying back out into space with no way to return. Too steep, and the heat shield will fail. They'll burn up. The re-entry corridor is narrow, only a few degrees margin for error. They need to make a correction. But here's the problem. The lunar module's guidance computer has been shut down to save power. They need a way to navigate without it. This is where Jim Lovell's experience pays off. Years ago, on Apollo 8, he and his crew developed a backup navigation technique. If the guidance computer failed, they could align the spacecraft using the Earth's terminator, the line between day and night, visible through the spacecraft's optics. It was a just-in-case procedure, something they hoped they'd never need. But now they need it. Houston reads up the procedure. Lovell will use the alignment telescope to sight on the Earth's terminator. By positioning it precisely in the crosshairs, they can establish their attitude. Then they'll do a manual burn of the descent engine. 3 men working together, Jack calling out the time, Fred controlling pitch, Jim controlling roll and working the throttle. It's dangerous, it's risky, but it's all they've got.
Okay, ready for the burn? Mark, ignition. The engine fires. The spacecraft responds. Pitch is good, roll is good. 5, 4, 3, 2, 1. Shutdown. Nice work, guys. The burn is perfect. They've corrected their trajectory. They're lined up for re-entry. But they're not out of the woods yet. Not by a long shot. They're still more than a day from home. And now they have to start thinking about re-entry itself. The command module has been shut down for nearly 3 days. It's frozen solid. Ice coats the windows and walls. Moisture has condensed everywhere. And they need to power it back up. This has never been done before. No one has ever powered up a command module from scratch in space. The startup procedure normally takes hours and requires ground power. They don't have hours. They don't have ground power. They have the lunar module's limited batteries and a ticking clock. In Houston, John Aaron, the ECOM who saved Apollo 12 from a lightning strike, is working on the power-up procedure. He's thinking through every system, every switch, every circuit breaker, trying to find the absolute minimum needed to get the command module functional for re-entry. His procedure has to work. There's no second chance. The new power-up sequence is radioed to the crew. Jack Swigert, as command module pilot, will handle this. It's his spacecraft. He knows every switch, every system. But he's nervous. The command module has been soaking in the cold for days. What if the electronics are damaged? What if moisture has shorted something out? They won't know until they try. Okay, Houston, we're starting the power-up. Roger, Jack, we're with you. Switch by switch, system by system, the command module comes back to life. The batteries are connected, voltage reads nominal. The flight computer boots up. It's working. The guidance system initializes. Navigation is online. Communication systems are checked. Everything is functioning. Against all odds, the command module has survived its frozen hibernation. But the heat shield, that's still an unknown. They won't know if it's intact until after they jettison the service module. 4 hours before re-entry, it's time to say goodbye to part of the spacecraft. The service module, which has been attached since before launch, is about to be jettisoned. Jim Lovell and Fred Haise, still in the lunar module, will get their first look at the damage. Okay, Houston, we're ready to jettison the service module. Roger, you're clear to jettison. Jack Swigert throws the switch. Explosive bolts fire. Springs push the service module away. It drifts out in front of the spacecraft, rotating slowly, and the crew gets their first look at what happened. Oh my God, that whole side is blown out. The entire panel is gone. Lovell can see inside the service module, see twisted metal, see damaged components hanging out. There's whole panel blown out from the high-gain antenna down to the engine bell.
Fred Haise is snapping pictures as fast as he can. Looking at this damage, the crew realizes how lucky they are to be alive. If that explosion had happened anywhere else, if it had ruptured a fuel line or damaged the main engine, they'd already be dead. For the first time, they understand the full magnitude of what they survived. But now a new worry sets in. The explosion was powerful enough to blow off a 13-foot panel. Could it have damaged the command module's heat shield? The heat shield is on the opposite end of the command module from the service module, but maybe debris hit it. Maybe the shockwave cracked it. They can't see the heat shield. It's still covered by the service module's nose section. They won't see it until that section is jettisoned, and by then it'll be too late to do anything about it. They're committed. They have to trust that the heat shield is intact. They have no other choice. 1 hour before re-entry, it's time to leave the lunar module. Aquarius has been their home for 4 days. It's kept them alive, kept them warm, well, relatively warm, provided power and oxygen and water. It's been their lifeboat. But now they have to abandon it. The lunar module cannot survive re-entry. Only the command module has the heat shield needed to plunge through the atmosphere. Jim Lovell is the last to leave. He takes one final look around. This spacecraft saved their lives. "Farewell, Aquarius," he says quietly, "and thank you." He closes the hatch. Jack Swigert throws the jettison switch. The lunar module drifts away, tumbling slowly, its job done. It will burn up in the atmosphere, a shooting star, a fitting end for humanity's most reliable spacecraft. Now there are 3 men in the command module. It's cramped, it's cold, but for the first time in 4 days, they're in the spacecraft designed to bring them home. Re-entry is 30 minutes away. On Earth, recovery forces are in position. Aircraft carriers, helicopters, rescue swimmers, all standing by in the Pacific Ocean. In Houston, mission control is packed. Every console is manned. Every back room is full. Flight controllers who've been working around the clock are still at their stations. They've done everything they can. Now it's up to physics and luck. 13, this is Houston. We show you on the proper trajectory. Everything looks good from here. Roger, Houston. We're ready. The command module hits the upper atmosphere. Friction begins to build. The outside of the spacecraft starts to heat up. 1,000 degrees, 2,000 degrees, 5,000 degrees. The heat shield, a thick layer of ablative material, is doing its job, burning away in a controlled manner, carrying the heat away from the crew capsule. But inside, the crew doesn't know if it's working. They feel the deceleration, feel the G-forces building. 1G, 2Gs, 3Gs, 4Gs, 6Gs. They're pressed into their seats, barely able to move. And then the G-forces peak and start to decline. They're through the worst of it. The heat shield has held. But they're not down yet. Around the spacecraft, superheated plasma is building up, a glowing sheath of ionized gas. This plasma blocks all radio signals. For 4 minutes, Apollo 13 will be in total communications blackout. Mission Control can't hear them, can't track them, can't help them. All they can do is wait and hope. The clocks tick, 1 minute into blackout, 2 minutes, 3 minutes, 3.5 minutes. They should be coming out any second now. The tension in Mission Control is unbearable. Odyssey, Houston, standing by, over. Nothing but static. Odyssey, Houston, over. Still nothing. They're past the expected time. Something is wrong. Odyssey, Houston, standing by. And then, faint at first, a voice breaks through the static. "Okay, Joe." Jack Swigert's voice, calm and professional. The room erupts. Applause, cheers, tears. Men who've been holding it together for 4 days finally let their emotions show. The spacecraft is through the blackout. They're alive. Moments later, the drogue chutes deploy, slowing the spacecraft. Then the 3 main parachutes blossom, huge orange and white canopies. On television screens around the world, people watch as Apollo 13 descends gracefully toward the Pacific Ocean. The parachutes are fully deployed, Everything looks perfect. In Mission Control, grown men are crying, hugging each other, shaking hands. Gene Kranz stands at his console, arms crossed, allowing himself the smallest of smiles. They did it. They actually did it. The flight controllers in mission control, many of them in their 20s, many of them just a few years out of college, demonstrated a level of skill and composure that seems almost superhuman. They made split-second decisions that determined whether the crew lived or died. They coordinated dozens of different systems and teams. They created procedures on the fly. They never stopped working, never stopped thinking, never stopped fighting for the crew. Gene Kranz, their leader, would later write a book titled "Failure is Not an Option," though he admitted he never actually said those words during the mission. But the sentiment was real. Failure wasn't an option because failure meant death. So failure was simply not acceptable. They would find a way. They had to find a way. And they did. In the years since Apollo 13, the mission has taken on a mythic quality. It's been the subject of books, documentaries, and a major Hollywood film. The phrase, "Houston, we have a problem," has entered the popular lexicon, though the actual words were, "Houston, we've had a problem." The story resonates because it's fundamentally a story about overcoming adversity, about people coming together to achieve the impossible, about hope and determination and the refusal to give up. It's a story that reminds us what humans are capable of when we're at our best. But Apollo 13 also taught NASA hard lessons. The accident investigation revealed systemic problems, quality control issues, communication failures, design flaws that should have been caught. NASA took these lessons seriously. Changes were made, testing procedures were improved, oversight was strengthened. The oxygen tanks were redesigned, the electrical systems were reviewed. Every spacecraft and every component was examined with fresh eyes. Could this fail? What if it does fail? How do we prevent it? How do we mitigate it? The culture of complacency that had been creeping in, the sense that spaceflight was becoming routine, was shattered. Space would never be routine. Space would always be dangerous. And that meant eternal vigilance was required. The Apollo program continued after Apollo 13. Apollo 14 successfully landed at Fra Mauro, the site Apollo 13 was supposed to reach, and completed the scientific mission. Alan Shepard, America's first astronaut, walked on the moon and famously hit golf balls in the low gravity. Apollo 15, 16, and 17 pushed even further, with longer stays on the surface, the lunar rover to explore greater distances, and more sophisticated scientific equipment. The program ended with Apollo 17 in December 1972. 12 men had walked on the moon. Hundreds of pounds of samples had been returned. Humanity had achieved something unprecedented in history. And Apollo 13, the mission that didn't land, became one of the most important flights of all. Because Apollo 13 proved that space exploration could be dangerous and survivable, that setbacks could be overcome, that when something went wrong, brilliant people working together could fix it. Before Apollo 13, there was a fear in NASA that any major failure in space would be fatal, that once disaster struck, the crew was doomed. Apollo 13 proved that wasn't necessarily true. With good design, good training, good procedures, good communication, and good people who refused to give up, even a catastrophic failure could be survived. That lesson gave confidence to future programs, the Space Shuttle, the International Space Station, the commercial crew programs. All of them benefited from the knowledge that space, while dangerous, could be survivable with proper preparation. The technological legacy of Apollo 13 is significant. The explosion and subsequent rescue mission drove improvements in spacecraft design, in life support systems, in contingency planning. The techniques developed to stretch consumables, to power down systems, to operate spacecraft in unexpected configurations, all of these became part of NASA's knowledge base. Future missions incorporated these lessons. Redundancy was enhanced, failure modes were analyzed more carefully. The what-if questions were asked more rigorously. Apollo 13 made the space program safer, even though it was itself a demonstration of how dangerous space could be. But perhaps the most important legacy of Apollo 13 is human. It's the demonstration of what people can achieve when they refuse to accept defeat. Jim Lovell, Fred Haise, and Jack Swigert could have panicked. They could have given up. They were hundreds of thousands of miles from Earth in a dying spacecraft. The odds were against them. But they didn't panic and they didn't give up. They stayed calm, followed procedures, worked with mission control, and did everything in their power to survive. The flight controllers could have been overwhelmed by the complexity of the problems they faced. They were dealing with failures that had never been anticipated, creating solutions that had never been tested. But they didn't get overwhelmed. They broke the problems down. They worked them one at a time. They communicated clearly. They made decisions based on data and analysis, not emotion. The engineers could have said, "It's impossible. We can't make square canisters fit round holes. We can't power up a frozen spacecraft. We can't navigate without computers. We can't get them home." But they didn't say impossible. They said, "How can we do this? What do we have to work with? What are the constraints?" And they found solutions. Time and again, they found solutions. That's the spirit of Apollo. That's the spirit of exploration. Not accepting limits, not accepting defeat, finding a way, making a way, even when no way seems to exist. This spirit isn't unique to NASA or to spaceflight. It's a human quality, something we're all capable of. The Apollo 13 rescue wasn't the result of superhuman abilities. It was the result of ordinary people with extraordinary training and motivation doing their jobs to the absolute best of their abilities. And that's inspiring, because it means we're all capable of more than we think. When challenged, when pushed to our limits, when facing seemingly impossible situations, we can surprise ourselves with what we achieve. Today, more than 50 years after Apollo 13, we're entering a new era of space exploration. Private companies are launching astronauts. Plans are being made to return to the Moon and eventually to go to Mars. New spacecraft are being designed, new technologies developed. But the lessons of Apollo 13 remain relevant. Space is still dangerous. Things will still go wrong. And when they do, the response will determine the outcome. Good design, good training, good procedures, good communication, and most importantly, good people who refuse to give up. These are the ingredients for surviving disaster. These are the ingredients for success. The story of Apollo 13 reminds us why we explore. Not because it's easy, but because it's hard. Because the challenges force us to be better, to be smarter, to be more creative. Because overcoming those challenges proves what we're capable of. Because pushing the boundaries of the possible expands those boundaries for everyone. Jim Lovell never walked on the moon, but his journey was just as important as those who did. Maybe more important, because it demonstrated that exploration isn't just about success. It's about perseverance in the face of failure. It's about bringing people home. It's about never giving up. In mission control on April 17, 1970, after the crew was safely aboard the USS Iwo Jima, Gene Kranz gathered his team. They were exhausted. They had been working for 4 days with minimal sleep, living on coffee and adrenaline. But they were also elated. They'd done the impossible. Kranz looked around the room at these young men, many of whom would go on to become legends in the space program, and he said, "This was a moment when we had to believe in ourselves. We had to believe in each other. We had to believe that we could solve any problem, overcome any obstacle. And we did. We brought them home. That's what we do. That's who we are. We are NASA. And failure is not an option."
Those words, whether exactly spoken that way or not, captured the essence of what happened during Apollo 13.
A team of dedicated professionals, faced with an unprecedented crisis, refused to accept defeat. They worked the problem. They found solutions. They brought 3 men home from the edge of space and the edge of death. And in doing so, they created a legacy that continues to inspire, a legacy of competence, determination, and the unshakable belief that with enough ingenuity and effort, any problem can be solved, any challenge can be overcome, any crew can be brought home. Apollo 13 was a successful failure, as Jim Lovell later called it. It failed in its primary mission of landing on the moon, but it succeeded in demonstrating the strength of the human spirit, the power of teamwork, and the incredible capabilities of a team united by a common goal. It showed that when people work together, when they communicate, when they trust each other and refuse to give up, they can achieve miracles. They can bring a dead spacecraft across 250,000 miles of space and land it safely in the Pacific Ocean. They can make square pegs fit round holes. They can navigate by the stars when computers fail. They can survive cold and thirst and exhaustion. They can do whatever it takes. That's the real story of Apollo 13, not the story of an explosion or a disaster, but the story of a rescue, the story of people at their absolute best, doing things that had never been done before, creating solutions in real time, never wavering in their commitment to bring the crew home. It's a story that deserves to be told and retold because it reminds us of what we're capable of. It reminds us that when faced with impossible odds, the human response should not be despair, but determination. Not surrender, but solution finding. Not giving up, but doubling down. 50 years later, the capsule Odyssey sits in a museum. Visitors can see the scorch marks on the heat shield, evidence of the fiery re-entry. They can see the cramped interior where 3 men lived for 6 days. They can imagine what it must have been like, cold and scared, and hundreds of thousands of miles from home. But they should also imagine the thousands of people on the ground who worked to bring that capsule home. They should imagine the flight controllers who never left their posts, the engineers who solved impossible problems, the astronauts who kept their cool when everything went wrong. They should imagine the Apollo 13 rescue not as one moment, but as hundreds of moments, each requiring skill and courage and determination. And they should remember that Apollo 13, this mission that went so terribly wrong, became one of NASA's finest hours precisely because of how the team responded to disaster. They turned failure into success. They snatched victory from the jaws of defeat. They proved that space exploration, while dangerous, is worth the risk because of what it reveals about human potential. We can go to the moon. We can survive catastrophe. We can solve any problem. We can do anything if we work together, if we refuse to give up, if we believe in ourselves and each other. That's the legacy of Apollo 13. That's why we remember this mission more than half a century later. Not because of what went wrong, but because of how it was made right. Not because 3 men went to the moon, but because 3 men came home. Not because the spacecraft worked perfectly, but because the people behind it worked perfectly, flawlessly, heroically. Apollo 13 is a testament to human ingenuity, perseverance, and the incredible things we can achieve when we dare to explore, when we face our fears, and when we never, ever give up. From the moment of the explosion to the moment of splashdown, Apollo 13 demonstrated that the greatest technology humans have ever developed isn't in the spacecraft or the computers or the rockets. It's in ourselves, our ability to think, to adapt, to overcome, to survive, and ultimately, to triumph. That's why we explore. That's why we continue to reach for the stars, because out there, beyond our world, we find not just new knowledge about the universe, but new knowledge about ourselves. We discover what we're truly capable of. And the story of Apollo 13 reminds us that what we're capable of is extraordinary. When 3 men were stranded in space, thousands of people worked around the clock to save them. And they did. Against all odds, against all expectations, they brought them home. And that victory, that triumph of human determination over circumstance, that successful failure, stands as one of the greatest achievements in the history of space exploration. Apollo 13 didn't land on the moon, but it reached heights that perhaps no other mission has reached before or since, heights of human courage, ingenuity, and the unbreakable will to survive. And that makes it a mission worth remembering, worth celebrating, and worth learning from for generations to come. If you enjoyed this, please consider subscribing for more. See you on the next one.